Guys, today we will try to compare the bending equation and the torsion equation. You have seen last time the bending equation is m by I by sigma v by y is equal to E by R. You know what are these terms? Okay, this is for a beam which is actually bent like this, where a moment is applied m, and you know that if you try to join this, it actually joins with an angle theta, and this, if you see the radius of this, that is the radius of curvature till this neutral axis. And if you want to find out the stress in any fiber, sigma b at a distance y, then it is given by m by I is equal to sigma b by y is equal to E by R, where Young's modulus, this is Young's modulus, this is radius of curvature, this is bending stress at the distance y from the central, from the neutral axis, and I is nothing but BDQ by 12 for rectangular sections. And if it's a circular section, suppose if it is a rectangular section, you write this as BDQ by 12. Suppose if it is a circular section, the moment of inertia is pi d to the power of 4 divided by 64. You need to remember this. Okay, please remember these two equations. Okay. For rectangular sections, it is BDQ by 12. And for circular sections, it is actually pi d to the power of 4 divided by 64. So that is the moment of inertia. So we want to compare this equation to equation of torsion. Equation of torsion. This is called as bending equation. Bending equation. People also may call it as flexure equation. Flex means what? Bend. So flexure equation. Flex andre ivaga show ಮಾಡೋದು ಅಂತ ನೀವು ಅನ್ಕೋತೀರಲ್ಲ. Okay. So this is flexure equation also. People may call it as flexure equation or bending equation. This is given by this equation. And let us see how this would actually compare to the torsion equation. How this would actually compare to the torsion equation. The torsion equation is given by this. It is given by this equation. Okay. Now, how is this? Okay, now you should understand what is this torsion equation. This is for a solid shaft which is applied with a torque T. So imagine that there was a fiber here AB, and after applying this torque, this B gets twisted. If I twist my hand like this, no, my hand is going like this. So we are trying to actually twist this shaft. The point B shifts from B to B dash. Okay. So this angle is known as the shear strain. And if you actually try to plot this change in angle, that would be equal to, that you would call it as theta, which is called as the angle of twist, which you are seeing it here. Okay, I think everybody knows that we have applied a torque T. So now this term is known, you know this theta term. And we know that in the case of the bending moment, we are applying a bending moment. In this case, we are applying a torque. So it is matching. Bending moment equation, you are applying a bending moment like this. Here you are applying a torque. And here, you have got this I, which is actually BDQ by 12. And here, this stands for, people write it as JP. JP stands for polar modulus. This is actually moment of resistance, polar moment of inertia. So that is for shafts, it is actually pi d to the power of, pi dq by 32. Sorry, this is actually the sum of these two, pi d to the power of 4 divided by 64 plus pi d to the power of 4 divided by 64, which is actually equal to pi d to the power of 4 divided by 32. So that is actually See, in most of the cases, for actually application of the torque, nobody uses a square shaft. Nobody uses a rectangular shaft. Everybody uses a circular. Shaft means circular. Suppose if somebody says shaft, nobody asks whether it's rectangular. Shaft means usually circular. It is actually the sum of the polar moment of inertia about the x-axis and y-axis. X-axis also the moment of inertia is same, pi to the power of 4 divided by 64, and y also it is actually pi to the power of 64. That is the moment of inertia about ixx. I just said no. In this case, for shaft, that's for circular sections, it is pi to the power of 4 divided by 64. So for shafts, it is the sum of these two, ixx plus iyy, which you get it as 2 times of this, which is actually pi to the power of 4 divided by 32. You just need to remember this equation. So you know T, you know JT. Now you know, in the case of bending, you have bending stress. In the case of torsion, you will have shear stress. You will have shear stress. So instead of bending stress, you have shear stress. And then now this bending stress is actually different for different fibers, which is at a distance from the neutral axis. Here, the shear stress is actually different for different fibers which are lying like this radially, okay, different radius. If you want the shear stress at the periphery of the shaft, you should actually substitute the radius as the radius of the shaft. So very similar to this y, where y is the distance from the neutral axis to which you want, where you want to measure the bending stress. Here also, if you want to measure the bending stress at the periphery of the shaft, then you should substitute this value as a radius of the shaft. Usually you substitute it as the radius of the shaft because the shear stress will be maximum at the periphery, because it will actually vary like this. Okay, so at the periphery of the shaft, it will be maximum. At R, it will be maximum shear stress. So you usually substitute R. So like this, you know M, you know torque. Instead of moment of inertia, you got polar moment of inertia. Okay, instead of bending stress, you got shear stress. Instead of this distance from the neutral axis to any fiber, you have got distance from the center to any radial fiber. And then instead of this Young's modulus, what is Young's modulus basically? Young's modulus is stress by strain. Okay, stress by strain. What is rigidity modulus? Shear stress by shear strain. Okay, so like this. Okay, shear stress. So shear stress is actually tau. Shear strain is gamma. Okay, so here there is bending stress. So you use this equation because bending stress leads to compression and tension. There's at the upper fibers there is compression, at the bottom fibers there is actually tension. So it is almost like bars under tension or compression. You use this Young's modulus equation. Here, since it is getting twisted, the shape is getting changed. So therefore, you can imagine if you can hold an eraser at one end and if you try to actually twist it, the shape gets changed. No? Basically, in the shaft, the molecules are actually getting twisted. So there is shear. So use this equation instead of using E, you are using G. And here you have the bending, this radius of curvature. Instead of that, what you use is length. So I think it may not actually exactly match. You don't have to compare it for any reason, but it will make it easier for you to remember this. Only extra thing along with this G is theta. Okay? Please everybody remember this equation. And is there any way can somebody actually suggest how can this be remembered? Is it seen? Okay, am I seen now? No?
I see.
Okay, all these equations are seen? Okay. Now, anybody can suggest how you can remember this equation? I think people have some tricks. I use this trick long back. Please see whether this tricks work for you. Who was the greatest musician in Tamil music industry? Huh? Raja. Who? Huh? A. Rahman? Okay, old one. Raja. Okay. So I want to ask him whether I can sing for him. Okay, I want to be a singer. Okay, I go and request him. So I make a sentence. May I sing for you? Sorry. May I sing for you? Sing for you, Raja. Okay. So here, this is M, bending moment. This is BDQ back 12. This is sigma. Sing means this is sigma, guys. Don't confuse it. Sing and pro sing and sing is actually sigma. Sing is actually sigma. And this is for you. Sing for you. This is sigma for Y. So that means if you want the stress in any fiber, then you have to substitute that Y. Sing for you. And then India Raja. Okay, like this. So please remember this, and maybe with this equation you can solve. Okay? And now anybody can actually make an equation for this. Is this okay, or somebody has any other idea? If you want to write, okay. I don't know, I made this. My Hindi is not that good, but still I have made this. So please bear with me. This is okay. Okay, it may be funny, but I am asking you to save yourself. Okay? Tera towel ganda. So one extra thing. This, don't forget this theta. Okay? And then you put this equation like this. And this T stands for this theta, this is T, this is tau. This is not sigma, this is tau. Okay? And G, Nanda, this is G, rigidity modulus, and this is J, polar modulus of, okay, and this radius from the center, and L is the length of the shaft. Okay? With this, maybe you can remember these two equations, and the derivations are quite important, so please have a look at this. So with this, we'll try to solve numericals. Guys, very similar to this, moment at Newton meter. Here this torque as Newton meter. Here this add mm to the power of 4. Here also this is mm to the power of 4. And shear stress, bending stress is Newton per mm square or Newton per meter square. Here also it is Newton per meter square. It matches. These two equations in most of the ways matches. Okay? And you can definitely use this equation and solve some easy problems. Just you have to know this formula for JP. One of this is not given, you have to find. It's a very straightforward problems. We'll solve two numericals which are very easy. Okay?